Hey guys, today we're going to be starting chapter 12, which is thermodynamics. This is in our fluids and thermodynamics unit. Today is going to be a lot of chemistry review, so if you took chemistry already, then you're pretty much set. There are going to be a couple of new equations that we look at, but all of the concepts are going to be the same as you learned in chemistry when you learned gas laws. Starting with solids, liquids, gases, I'm not actually going to talk through these slides because I'm not trying to insult your intelligence. So if you don't know what solids, liquids, and gases look like on a molecular level, Google it, do some research on your own, find out, but I'm not going to sit here and lecture you through that. Basically, just gases have super quick moving molecules. Liquids have slower moving molecules that still slide around. And solids have molecules that are pretty stiffly bonded together. All right, so that's solids, liquids, and gases. Moving on. Other things you need to remember from chemistry are that the mass number equals protons plus neutrons. That 1 mole is 6.02 times 10 to the 23rd particles. You also need to know how to do that conversion. And that the molar mass is the mass of 1 mole of a substance. You need to know how to find molar mass. If you don't know how to find molar mass or convert moles to particles, please email me. I can send you some other videos I've done over those topics, but you should have already learned that in chemistry. All right, on to the actual part of the lecture that is new. So for today and tomorrow, we're going to be talking about ideal gases and thermodynamics for ideal gases, which are highly compressible, so they can have a variable volume. And today, what we're mostly going to be looking at is the temperature. You should remember from chemistry that temperature is based on the kinetic energy of the molecules. And the equation for that relationship is shown right here on this slide. Temperature equals 2/3 times the average kinetic energy divided by this value that is called Boltzmann's constant, 1.38 times 10 to the negative 23rd joules per Kelvin. Note that this constant does use the Kelvin scale for temperature. So when you find temperature using this formula, you are finding the Kelvin version of temperature. Something that this formula is useful for is calculating for the total energy held in a gas. So if we look at that equation that we just had that said temperature equals 2/3 average kinetic energy divided by the Boltzmann constant, you can solve that around for the average kinetic energy. So the average kinetic energy equals 3/2 times temperature times Boltzmann's constant. And that was the average kinetic energy for one molecule, or one atom. So if we wanted to find the total energy of a gas, the total thermal energy, you would multiply this by the number of atoms or molecules. So that would give you that the total energy is 3/2 N times the Boltzmann constant times temperature. And we could also use this to talk about a change in energy, which would be work, but the change in energy that is thermal would be 3/2 N kb times the change in temperature. So you could use this to calculate how much energy you need to raise or lower the temperature of a specific gas. All right, so let's use these ideas in this example. It says a large bedroom contains about 1 times 10 to the 27th molecules of air. If we model the air as an ideal gas, how much energy is required to raise the temperature of the air in the room by 5 degrees Celsius? So we use that equation. The change in thermal energy is equal to 3/2 times the Boltzmann constant times N times delta T. I think those variables are out of order, but commutative property of multiplication says it's fine. So we'll do change in energy equals 3/2. Oh, I just wrote 3/8. 3/2. The Boltzmann constant we said is, let me look it up real quick. Boltzmann's constant is 1.38 times 10 to the negative 23rd joules per Kelvin. The number of molecules is 1 times 10 to the 27th. and the change in temperature is 5 degrees Celsius. You should change that to Kelvin. So a change of 5 degrees Celsius is also a change of 5 degrees Kelvin. You can convince yourself of that using the formula for that conversion, which says Kelvin equals degrees Celsius plus 273. So a change in the Kelvin is just going to correspond to the same change as in Celsius. So that works out nicely. If that doesn't make sense to you, actually pick some numbers in Celsius, change them by 5 degrees, and see what happens to the corresponding Kelvin temperatures. You'll see that it's also a change of 5 degrees. All right, so then you just got to slap that sucker into a calculator. You do 3/2 times 1.38 times 10 to the negative 23rd times 1 times 10 to the 27th times 5. And my thing says I get a nice, lovely syntax error. It's because I didn't do 3/2. Okay, so we get 103,500. And that is in joules, quite a lot of joules. All right, next up with temperature is molecular speed. So in an ideal gas, the theory is that all of the molecules are moving randomly, and they can have variable speeds. We were looking at the average kinetic energy, the average, which would be based on the average speed. So that value will be useful, but one molecule in and of itself doesn't necessarily have to have that speed. There's a distribution of speeds, and we're taking the average. So this graph here shows what could be a distribution of the speeds of molecules that are at 20 degrees Celsius for nitrogen 2 molecules, with the average right here at 510 meters per second, right there. And you can see that most of the molecules are in that 500 to 600 range. Molecules at the extremities, there's very few of them as a percentage. But also notice that these speeds are crazy high. 510 meters per second is a very high speed for like an everyday object as we would consider it. So these molecules are moving very, very quickly. All right, so on this slide, we are going to derive down an expression for that speed, which is called the root mean square speed. Because it's probabilistic, we're determining like the average, and the way we're doing that average is with the root mean square, which is a statistics thing, won't go into it. But this is like the average speed. So if we take the average kinetic energy of the molecule, we know from our previous equation that the average kinetic energy was 3/2 times the Boltzmann constant times the temperature in Kelvin. And we also know that kinetic energy equals 1/2 mv squared. So we'll say 1/2 mv squared equals 3/2 kBt. You can solve this for velocity. Multiply both sides by 2 and divide by m. So times 2, divide by m, times 2, divide by m. And you'll get v squared equals 3 kBt over m, and you have to square root the whole shebang to get just the velocity. Velocity equals 3 kBt over m. So that's the root mean square velocity. It's the root mean square, not just straight up velocity, because it is an average that we're taking using a square root. And as stated on the slide, make sure that when you do temperature here, you're using Kelvin. All right, here's an example. It says most of the Earth's atmosphere is the gas nitrogen, which consists of molecules of N2. At the coldest temperature ever observed on Earth, negative 95 degrees Celsius, what is the root mean square speed of the nitrogen molecules? Does the temperature at the Earth's surface ever get high enough that a typical molecule is moving twice this speed? So let's look at the first case, the coldest temperature ever. What's the root mean square speed? So we get velocity RMS equals the square root of, and this is 3 times the Boltzmann constant times temperature divided by mass, which looks like just plug and play pretty much. So we'll do 3 times the Boltzmann constant, which is 1.38 times 10 to the negative 23rd. The temperature has to be in Kelvin, so we do negative 95 plus 273 will get you, let's see, 178. And then you divide that by the mass. But you have to find the mass of N2, which, let me tell you, is a process. So first thing you need to know is that N2 would be 14.007, which is from the periodic table, times 2, 28.014, but that mass is in AMU, atomic mass units. So you're going to need to be able to convert that to kilograms, the SI unit. And the conversion is that 1 AMU, which is also abbreviated as a U for your AP physics sheet, equals 1.66 times 10 to the negative 27th kilograms. So you're going to do 28.014 times 1.66 times 10 to the negative 27th to get 4.65 times 10 to the negative 26th. And that's what will go on the denominator of your square root. And then you'll calculate that out to get the speed. And the speed you get is 398 meters per second. And then the second question asks, does the temperature of the Earth's surface ever get high enough that a typical molecule is moving at twice this speed? To be moving twice the speed, the temperature has to be 4 times as big, because this is a square root relationship. So we'd have to have 4 times our 178 Kelvin, which is 712 Kelvin. And if you subtract back off the 273 to make that Celsius, that's 439 degrees Celsius, which is definitely way lower than this observed speed on Earth. Sorry, the highest observed temperature on Earth, 54 degrees Celsius. All right, so the answer to that second question is no. The temperature will never get that high. All right, guys, thanks for watching. Let me know if you have any questions. You do have a new homework posted in Google Classroom that has some questions covering this, so go get to work on that.